On the night of 25th of June 2024, people camping on the grasslands of Inner Mongolia saw a bright streak race across the sky. It was the return capsule of China's Chang'e 6 mission, dropping through Earth's atmosphere and landing in the sand. Inside sat 1.9 kilograms of dust and rock collected from the far side of the moon, the half that never faces us and is hard to reach with radio signals. No one had ever brought back samples from there before. Now those pieces of lunar ground were resting in a steel container, waiting to be studied. In the next few minutes, we'll open that story box together and find out what the rocks reveal, and how the answers might shape the next era of space travel. China's road to the moon began quietly in 2007, when the Chang'e 1 orbiter set off to photograph every crater and valley from pole to pole. 3 years later, Chang'e 2 swept in lower and snapped sharper pictures, proving the country could steer a spacecraft with pinpoint accuracy, and even chase an asteroid after its main job was done. The next big step came in 2013. Chang'e 3 eased down onto the near side and rolled out the first Chinese rover, Yutu-1, which drilled into gray basalt and sent home panoramic views. 6 years later, the sequel, Chang'e 4, did something no one had managed before. It landed on the far side, inside Von Karman crater, and kept in touch with Earth through a relay satellite parked beyond the moon. Its rover, Yutu-2, is still crawling today, using ground-penetrating radar to peel back layers of buried lava. In 2020, the tempo quickened. Chang'e 5 raced to the near side, scooped 1.7 kilograms of rock, the youngest samples ever collected, and returned them only 23 days after launch. Finally, on 25th of June 2024, Chang'e 6 touched down in the vast South Pole Aitken Basin, grabbed almost 2 kilograms of farside soil, and dropped them safely onto the grasslands of Inner Mongolia. 6 missions in 17 years have turned China from a newcomer into a sample return veteran. And the story is still unfolding with Chang'e 7 and a planned international research station waiting in the wings. Picture a robot the size of a coffee table, trundling across a landscape no human eye had ever seen in person. That is Yutu-2, the rover that rolled off Chang'e 4's lander on 3rd January 2019 and became the first visitor to explore the moon's far side. Its playground is Von Karman crater, a 180-kilometer wide scar near the center of the vast South Pole Aitken Basin. The crater floor looks flat and gray on camera, but Yutu-2's instruments reveal a hidden, much older story. Twice a day, the rover switches on its ground-penetrating radar and sends radio pulses 200 meters beneath the surface. The reflections come back like an X-ray, 3 thick layers of solidified lava stacked on older impact debris, each sheet poured out at a different time. One layer is so rough and blocky that scientists think lava may have oozed up through cracks long after the basin formed, keeping this part of the far side volcanically alive far longer than anyone guessed. Yutu-2 also shows that the soil, or regolith, is far deeper here than on the Apollo sites, at least 12 meters, and sprinkled with tiny spheres of silicate glass formed in ancient fire fountain eruptions. The rover has logged more than 2,000 meters of travel and survived over 70 harsh lunar nights, when temperatures plunge below minus 170 degrees Celsius. Every new drive rewrites the map of the far side and hints at rich, untapped geology lying just beneath our distant neighbor's skin. China's Chang'e 5 mission was a sprint. Launched in November 2020, it spent just 2 days on the lunar surface, drilled and scooped 1.73 kilograms of soil from a volcanic plain called Oceanus Procellarum, and raced the treasure back to Inner Mongolia 23 days after liftoff. What looked like an engineering stunt has since turned into a science goldmine. First came the age test. Tiny crystals inside the basalt were dated at about 2 billion years old, 500 million years younger than the youngest Apollo rocks. That single result rewrote lunar history. The moon did not cool down as early as textbooks claimed. Its volcanoes were still burping lava when life on Earth was already complex and crawling onto land. Then researchers spotted something no one had ever cataloged, a clear column-shaped phosphate they named Changesite-Y. The grains are smaller than a sesame seed, yet they carry global weight because they trap helium-3, an isotope prized for future fusion reactors. Early measurements show the surrounding soil holds 10 to 100 times more helium-3 than comparable Apollo samples, hinting that Oceanus Procellarum may be one of the richest spots for harvesting this fuel. Water was the next surprise. Spectrometers found hydroxyl, essentially water's chemical fingerprint, running up to 120 parts per million. That's bone dry compared with Earth, but wetter than scientists expected for sun-blasted lunar soil. The finding supports the idea that solar wind hydrogen can mingle with oxygen in moon rock to make trace amounts of water, a process that could eventually supply future habitats with air and rocket propellant. The rock cache is still being opened grain by grain. In 2025, China began lending milligram-sized portions to foreign labs, and each new analysis, magnetic clues here, unusual titanium levels there, adds fresh pages to the moon's unfinished autobiography. Chang'e 5 set out to grab samples. Instead, it grabbed headlines and widened every question we thought we'd answered about our nearest neighbor. When researchers finally opened the Chang'e 6 sample boxes in late 2024, they found volcanic history trapped in miniature. Most fragments are dark basalts, but lab dating revealed two very different birthdays. One chip formed about 4.2 billion years ago, just 300 million years after the moon itself. Another batch solidified 2.8 billion years ago, showing the far side kept erupting lava 1.4 billion years longer than many models allowed. Chemistry tells the next chapter. The ancient rock is packed with heat-producing elements like potassium and thorium, whereas the younger basalt comes from a mantle source drained of those ingredients. Somehow, magma still rose after its internal heating coils ran low, forcing scientists to rethink how the moon stayed warm inside. Tiny magnetic grains inside the 2.8 billion year sample add another twist. They record a lunar magnetic field of 5 to 21 microteslas, comparable to Earth's surface field today. That rebound hints that the moon's core was still churning, perhaps driven by a deep magma ocean, or by the moon's slow wobble around Earth. Water, or the lack of it, delivers a further surprise. Heating the grains in vacuum ovens showed less than 2 micrograms of water per gram of rock, several times drier than near-side soils. The result backs computer models suggesting the giant impact that formed the moon splashed volatile-rich melt toward the hemisphere that now faces Earth, leaving the far side parched. Perhaps the most tantalizing clues lie in a few coarse, pale fragments that do not match ordinary basalt. If tests confirm they are pieces of the deep mantle or ejecta from the colossal South Pole Aitken impact, Chang'e 6 will have delivered humanity's first direct samples of the moon's interior. Those pieces are now the hottest tickets in planetary science, with laboratories worldwide queuing for the tiniest pinch. First, the water. Spectrometers on the Chang'e 5 samples show that the soil from Oceanus Procellarum holds between about 30 and 120 parts per million of hydroxyl, the chemical tag for water, a bigger dose than most Apollo sites ever revealed. While that sounds dry by Earth standards, on the moon every molecule counts. Frozen or chemically locked-in water can be split into oxygen to breathe and hydrogen to fuel rockets. NASA is already designing pipes and furnaces that could tap ice around the lunar South Pole as early as the late 2020s, turning the moon itself into the filling station for deeper space flights. China's upcoming Chang'e 7 lander will scout those polar craters, so the far-side samples we just opened are a dress rehearsal for using local resources rather than hauling tons of supplies up from Earth. Now the helium-3. Solar wind has peppered the lunar surface with this rare isotope for billions of years. Chang'e 5 soils carry roughly 5 to 10 parts per billion, several times richer than most Earth ores. Helium-3 is prized because it can drive a kind of nuclear fusion that makes almost no radioactive waste. A single ton, if we could ever fuse it efficiently, would release about as much energy as burning 15 million barrels of oil. That prize has lured startups such as Inner Mongolia, which in May 2025 rolled out a prototype regolith harvester built to scoop 100 tons of soil an hour. China, the United States, and now private companies all see the isotope as a potential cornerstone of a moon-based economy. Water keeps people alive and rockets moving. Helium-3 could someday keep entire power grids running. Together, these two ingredients turn a gray, dusty world into real estate worth racing for. On April 24, 2025, China Space Day, the National Space Agency opened its Rock Vault to the world. Officials announced that milligram-sized portions of Chang'e 5 soil would be loaned to 7 institutions in 6 countries, among them Brown University, SUNY Stony Brook, the Open University in Britain, and labs in France, Germany, Japan, and Pakistan. Each team receives just enough dust to fill a sugar packet and must return any unused grains after 2 years, but the gesture breaks new ground. It is the first time China has let foreign scientists handle its lunar treasure. The loans arrive despite lingering political frictions. Because U.S. law bars NASA from direct partnerships with China, the samples travel under a special scientific purpose exemption brokered through university channels. Still, the move signals Beijing's intent to turn lunar science into a bridge rather than a battleground. By the time Chang'e 7 touches down near the South Pole, dozens of international researchers will already have left their fingerprints, figuratively speaking, on Chinese moon rocks. China's next lander-rover combo, Chang'e 7, is scheduled to launch in 2026 and dive straight for the moon's south pole. It will arrive as a 4-piece fleet: an orbiter to relay signals, a lander, a small rover, and a hopping probe designed to leap into permanently shadowed craters where sunlight never reaches. Those craters are thought to hide water ice mixed with dust. Chang'e 7's cameras, spectrometers, and an international suite of 6 guest instruments will map the ice, sniff for volatile gases, and test whether the soil releases water when gently heated. Roughly 3 years later comes Chang'e 8. Instead of just collecting data, it plans to build. The lander will carry a 3D printing experiment that mixes lunar soil and resin to make bricks, plus a sealed mini biosphere to see how hardy plants and microbes cope with the 2-week lunar day and the 2-week deep freeze night. If those demos succeed, China will have proven 2 pillars of a live off-the-land strategy: harvest local materials for construction and recycle air and water inside a closed habitat. Both missions feed directly into the International Lunar Research Station, ILRS, a joint China-Russia-based concept now courting partners from Asia, Europe, Africa, and South America. The roadmap calls for robotic construction between 2030 and 2035, followed by crewed stays late in the decade. Power would come from solar arrays and a small nuclear reactor. Pressurized labs would cluster near a ridge with near-constant sunlight, yet quick rover access to ice-rich craters. If the schedule holds, the South Pole Plateau where Chang'e 7 lands could, within 10 years, sprout the metal frames and inflatable domes of humanity's first multinational moon base. China's sample return missions have done more than fill museum cases. The far side and near side rocks extend the moon's volcanic timeline by 1 billion years, prove that water and helium-3 are spread unevenly across its face, and hint that the mantle itself may lie within shovel range. Those discoveries redraw textbooks, but they also tilt the future. Ice can fuel rockets, basalt can be 3D printed into landing pads, and helium-3 dangles the promise of clean power. With Chang'e 7 and 8 already on the manifest and an international research station taking shape on the South Pole Ridge, China's rock boxes are no longer souvenirs. They are blueprints, quietly turning the moon from a place we visited into a place we may soon call home. Thank you for watching. For more content, like and subscribe.